Hi, welcome to the Signal Pad. I have a really exciting episode for you guys today. We'll be taking a look at Teledyne LeCroy's 100 GHz, 240 gigasample per second oscilloscope. Yes, you heard that correctly. This is 100 GHz of real-time bandwidth sampled at 240 gigasample per second, again in real time. No one has ever built an oscilloscope this fast before. This is an incredible accomplishment. This is of course done via LeCroy's patented frequency interleaving technique and a whole slew of custom ASICs designed by Teledyne LeCroy as a whole system. Now unfortunately I don't have that scope here in my lab for a few reasons. First of all, it costs $1 million. That's right, this is a $1 million oscilloscope. So having it around is going to be a little bit difficult, and also there are not that many of them in the first place because it's just become available. And also it is quite difficult to test a 100 GHz oscilloscope. If you want to push it to its limit, you have to generate tones at 100 GHz. There are a few different ways of doing that. I wouldn't have really been able to do it here in my lab. So I'm going to do something even better. We're going to go to Teledyne LeCroy and we're going to take a look at the oscilloscope. First, we're going to hear from the inventor of this technique exactly how it works. He's going to explain it to us via block diagrams and how the system is put together. And then we're going to do something unheard of. We're going to do a teardown of the 100 GHz oscilloscope. How awesome is that? And then after that, we're going to put it back together and then we're going to try and do some tests on it. And we have come up with a couple of different really interesting tests that we can do on the scope to push it to its limits and to show you what an incredible instrument it actually is. And then finally at the end of the video, I also have a complete factory tour because these scopes are built and assembled here in the United States. So I can just drive there and they were kind enough to invite me over to do this whole episode for you guys. So it's pretty awesome. It's the world's first look at really looking at the internals of the 100 GHz oscilloscope. So let's start with Pete, who's going to explain to us exactly how it works, and then we're going to go through the experiments and so on. And don't forget to watch the end of the video, which is going to be the factory tour. So let's go.
Hi, my name is Pete Popolakis at Teledyne LeCroy, and I'm going to briefly speak about how our 100 GHz oscilloscope is designed. So to start with, I'm going to describe first how a 36 GHz scope channel works. So basically in an oscilloscope we have a signal coming in, we have a front-end amplifier, and we have many track and holds. These generally in an oscilloscope we design the front-end amplifier and the track and holds in a single chip. We call this chip an MSH. An MSH takes the data. It actually has, in its package, it has a coaxial connector. So there's a coax coming in, it lands on the package to maintain the 36 gigahertz of bandwidth, and coming out of the MSH are multiple tracked and held outputs. These all go to an ADC. The ADC in our current parts is a 40 gigasample per second ADC. And in this type of architecture, we would use 2 of them to get to 80 gigasamples. And then these all drive high-speed memories. So I'll just draw this as a bank of memories here. And we call these MAMs.
So in your design, are the track and hold amplifiers and ADCs different individual ICs connected on a PCB, or are they single monolithic ASIC part?
So this would be a single part.
Mm-hmm.
The ADC is a single part, and there would be 2 of those single parts. The MAMs would be many such parts. All of these parts in an oscilloscope, and I'm leaving out one piece, which is the MTT. The MTT controls the time base, basically controls the acquisition system, and also supplies the trigger. So there's something that comes out of here that supplies the trigger. All of these chips are not publicly available and are all custom designed by LeCroy. This particular part is an 8HP, IBM's 8HP silicon germanium process. These parts are 7HP silicon germanium. These are a combination of some Toshiba process, but they're all custom designed, which leads to some economic difficulties in oscilloscope design. That's why you pay so much for them when you buy them, because there's a lot of R&D that goes into these. Now, this acquisition system, which I just drew here, is 36 gigahertz, 80 gigasample per second. That today is about the maximum that anyone can achieve for an oscilloscope channel. And when I say that, what I mean is, as most people know, there are 3 people who make high-speed oscilloscopes, us being one of them. All 3 of these companies, this is about the max that they can achieve through just chip design.
So you're essentially describing the maximum single digitization possible at this particular speed being limited to about 80 gigasample per second. That's a single channel. That's what you have, the best you have in the industry right now in the oscilloscope domain.
Well, what I would say is, so let me describe a little bit more. So what I really was referring to is bandwidth. So the bandwidth of this channel right here is 36 gigahertz. Once you can get this 36 gigahertz of bandwidth to the track and holds and to the ADCs, you can actually interleave many ADCs. That's not really a limitation. You do have to have enough sample rate to support the bandwidth, but what I was really referring to is the 36 gigahertz of bandwidth.
Yes, the front end bandwidth is the limiting part, because the signals coming out of the sample and hold are no longer carrying the full signal bandwidth anymore. They're essentially, in a way, you could call them down converted because they're already multi-phase sampled. So you're saying that at that point you don't have a bandwidth limitation anymore, but that front end block that you've designed, that's your main limitation currently.
Right. Now, in many other types of electronics, we know we can reach, gigahertz, even terahertz speeds. Most of those applications are narrowband applications. It might be AC coupled applications. In an oscilloscope channel, we have to maintain DC. It's very broadband, so it goes DC all the way up to the bandwidth limit. And the signal fidelity requirements of an oscilloscope are probably a lot higher than most other types of electronics, since it's really supposed to be a TV set that you can use to view your signal. So now I'll erase this and show how that channel is implemented in a 100 gigahertz design. So basically what we have is, if you take a 36 gigahertz oscilloscope, I'm going to draw what I drew before for a scope channel as just a square now. Okay, so this square represents what I just had on the board before.
So that square represents a 33 gigahertz bandwidth, 80 gigasample per second ADC.
Correct. I'll just write 36 gig, 80 gigasample per second, and it has some amount of memory behind it. What we do in the 100 gigahertz design, and what we've done in many of our designs since about 2005, is we put a microwave front end in front of this. And in the 100 gigahertz oscilloscope, this microwave front end, the first thing it would consist of is a multiplexer. A multiplexer is a device that can pass multiple frequency bands out of its outputs. So in this particular case, this multiplexer would pass, I'm going to use rough numbers here, but DC to 33 gigahertz, let's say. This would be roughly 33 gigahertz to 66 gigahertz. And this would be roughly 66 gigahertz to 100 gigahertz. Okay? The DC to 33 gigahertz band goes directly into a scope channel, and it gets digitized just as it would normally. The other bands, just erase this here, go through a down converting stage, which I'll just draw stylistically as some kind of a mixer here. And those come out here. And so this band, which is taking the 33 to 66 gigahertz, would have a local oscillator set just above the band edge, like let's say 67 gigahertz. These aren't the exact numbers, but roughly. And so coming out of this, the IF port of this down converter would be 1 to, let's say, 34 gigahertz. It would actually be flipped over in frequency content. So you would take the band that would be, let's say, 33 to 66, and we place a local oscillator up here, and what you would see is this, and I'll just draw an arrow here. You would see the band coming out here, and just draw the arrow pointing backwards, and it would have the complex conjugate of everything. So this band now that's been down converted is within the bandwidth capabilities of this channel, so that gets digitized. And similarly for the 100 gigahertz band, I think you get the idea here. This might have a 101 gigahertz local oscillator. These three bands that come out in the oscilloscope channel now require some amount of processing to put everything all back together again. And so the first thing we would do, I'm just going to, I'm going to draw this like this. This is all done digitally, all done in software.
So those are DSP-based mixers, basically.
Yes.
So here you're trying to undo what you did in the analog domain in the digital domain.
Correct. Now, some of the challenges here digitally is, first of all, this diagram looks very nice and looks very simple, but in reality, there's quite a bit of signal degradation that occurs, signal fidelity degradation that occurs. Just to point out one in particular, whenever you send a signal through a very sharp filters like are shown here, you get a lot of group delay distortion, especially around the band edges. And that all has to be restored out here. So there's quite a bit of group delay correction. Also, before the bands are put together, since the phase is changing so rapidly throughout the band where the seam is, for the frequency seam, there's usually a crossover phase correction that guarantees that everything sums up substantially constructively, just so that it doesn't null itself, because then you are correcting nothing. The other sort of technical challenge is that this local oscillator that is used to mix, these would be the same frequencies, this would be analog and this would be digital, need to be phase aligned. So in some sense, we need to know the phase of the local oscillator here, over here, in order to put the signal together properly. We've done that many different ways in the past. One way that we did on early designs is we injected some divided down version of this into the signal path. So in our first scopes, we had an 11 gigahertz scope. The mixing frequency was 11.5 gigahertz. We injected a divided by 2 version of the local oscillator at 5.75 gigahertz, and that sat just above the band edge of the frequencies of interest. So that would be a pilot tone that would come along with the data. Obviously, we would filter that out prior to reassembly, but we would use that to determine the phase of the local oscillator for the digital mixing step here.
So the pilot tone will essentially also get digitized, and the DSP will then be able to pick up the digitized pilot tone, grab its phase, correlate it to its own down conversion DSP-based mixer, and then remove it. And that way you get phase coherence between your local oscillator analog LO and the DSP digital LO.
Yes, and that has really a lot of advantages because the pilot tone is coming along with the signal on each acquisition, so if there's drift and things like that, that's all accounted for. It's all in a single acquisition. We have the same local oscillator phase. Other ways of doing this are to lock the local oscillator to the sample clock of the system. So what that means is that the local oscillator frequency would be derived from a reference which was similar to a reference used in the sample clock generation. And in those type systems, those are nice because we can actually determine the phase from simply the memory location in the memory that shows up here.
What about the generation of the 67 gigahertz and 101 gigahertz tones that are used for the mixers? How are those generated? Are they generated with internal Yig oscillators that are multiplied up? How do you generate those?
So in earlier designs, we used a Yig-tuned oscillator, and again, those would be locked to they would use the same reference as the digitizing system. In the end, we found that we really didn't, well, number one, Yigs don't, at least commercially available Yigs don't go up
Right.
to 100.
You have to multiply them up, yeah.
Right, and so we used DROs and things like that. Most of this area of design is also very technically challenging and is also custom designed microwave stuff. Mostly the key components that are custom designed, certainly the multiplexer, which is very precise, and the mixers, and everything that occurs before the IF stage. So there's some amplifiers, variable gain amplifiers, and things like that that sit inside of this box.
So can you tell us a little bit about the different technologies? So the multiplexers at the front are microwave cavity components that are custom designed by LeCroy, Teledyne LeCroy, I assume?
No, we actually partner with a company, Phase Matrix, which is a National Instruments company. They have some guys there, most notably Dr. Paul Khanna, who is a world expert in microwave design. This particular diplexer that's in this scope is a mixture of strip line type microwave technology and some waveguide stuff, because usually the diplexers are they're planarized by having strip line, and really what you like to do is sandwich them on top of each other. So they have a waveguide that connects the two, because basically you strip off the 100 gigahertz first, and then you strip off the 65 gigahertz. So it's sort of in two stages, and they stick it on top of each other that way.
So one path travels in waveguide, the other path travels in microstrip.
Correct.
Right. Okay, that makes sense. And then what about the technology used for the mixers and the ASICs in the front end? Are they still in IBM's silicon germanium process, or are they in Teledyne's process now?
No, these would be designed in, I would say, more microwave-like electronics designs, and some of the parts are actually commercially available. The advantage here is once you're in this area of the design, you're AC coupled, which is a huge benefit. The scope, one of the big problems in the oscilloscope is, believe it or not, the carrying along with DC and having DC offset and things like that. That makes the scope quite challenging. The components on here, while they're high frequency, are AC coupled anyway, and they're relatively narrow band, maybe not narrow band by a microwave person's definition of the word, but are certainly small enough to be managed. But I would say that, so the key technologies here really are the mixer design. That's the stuff that is super challenging, I would say.
And this DSP that happens on the data coming from the ADCs, that happens in FPGAs?
I'm sorry?
The DSP, the mixers, that all your DSP processing, is that happening in the FPGAs?
No, that's a good question. It could, and it would be nice for that to be the case. What we typically do, one thing I didn't sort of explain about the scope acquisition system is, because it has memory inside of here, typically the way a scope acquisition works, even in a real-time oscilloscope, which as you know, is different from what we call a sampling scope or an equivalent time scope. So the real-time scope has to take data one point after another, but it does have an advantage of acquiring data into kind of a circular buffer, if you will, until the trigger system tells it to stop. So during the acquisition of the data, really nothing has to be done to it in real time. Once the trigger system tells it that it needs to stop, all of this data can be read out into a computer and processed in a regular PC. We've found that, in fact, using a multi-core, very high-speed PC motherboard is actually the most efficient way to do this processing. One thing you should note, in the processing of this kind of data, it's actually quite a lot of processing. It's about, I'm just going to use ballpark estimates, but it's probably about 5,000 to 10,000 floating point operations per point that gets out onto the screen. Today, that I don't believe could be done in a reasonably economical fashion in real time.
It would take several big FPGAs to construct
the
algorithm.
data coming out of this is 240 gigasample per second. So you would have to be doing 10,000 times 240 times giga flops.
A remarkable number of computations per second.
But we have this advantage where we can stop the acquisition.
So tell me a little bit about the triggering system. What is the highest signal that this 100G scope can trigger on?
Today, well, because of this architecture right here, as I mentioned before, there is in a general scope channel, there's a trigger system. So this oscilloscope, the way it's designed here, the highest frequency would be the frequency of this band right here, which would be 36 gigahertz.
But will the scope be able to trigger on signals that arrive on the other ADCs in this architecture? Or only the DC to 36 gigahertz ADC is the master trigger of the whole system?
One could, I mean, there is a trigger system in here, so you could generate some sort of complicated style of trigger, but in general, that wouldn't be that useful to an oscilloscope user, so we limit it to 36 gigahertz. We do have, in these kinds of scopes, many software triggering capabilities, so at least for trigger placement. And many of the applications for this type of scope don't really require triggering off of the signal, and furthermore, they don't even require precise alignment of the trigger to any kind of trigger event. But that could be done in software post-acquisition.
Now, the 100G scope obviously uses a 1mm connector in the front, which is attached to the body of the unit.
Yes.
There are challenges with often getting the signal of interest to the edge of the scope, especially if it's a 100 gigahertz signal.
Yes.
How do you deal with that in terms of, do you provide customers with calibrated 1mm cables that they can use if their setup is further from the edge of the scope? How do you handle a difficult situation like that? Because that's certainly different from having a 67 gig 1.8mm connector where cables are much cheaper, much longer, losses are much less.
Well, what we do provide is there's many features built into the oscilloscope for de-embedding these types of things. We have some technologies, we call them virtual probing technologies, where if you knew, let's say, the S parameters of your cable or your interface to the scope, you could de-embed that essentially from the real-time acquisition.
And that happens live. So your exactly. That's very critical because LeCroy has some of the most advanced computational algorithms live on their oscilloscopes across all the series of oscilloscopes you have. So this information you're describing happens live. You have a S parameter of the cable, you put it into the scope. Now the measurement you observe automatically has that cable de-embedded, so you don't even know you don't have to worry about it. It's transparent to the user.
Yes. So there you have it, the basic design of a 100 gigahertz Teledyne LeCroy oscilloscope. So thanks for listening, and I hope you learned something.
Hi, I'm Alan Blankman, product manager here at Teledyne LeCroy, and I'm going to give you a bit of a tour of some of the components used in the LabMaster 10-100zi 100 gigahertz oscilloscope.
Alright, so we saw before where Peter explained the block diagram of the entire oscilloscope architectures for the LeCroy lineup. So what is Alan going to do for us now, he's going to go and we're going to talk about the actual PCB design for every single component that goes in the foundation of all of the product lines they have. So we're going to start from, if you remember the block diagram, from the individual 36 gigahertz bandwidth 80 gigasample per second architecture, and then from there Alan's going to show us step by step to the 65 gigahertz architecture, and then finally to the 100 gigahertz oscilloscope. So Alan, go ahead and walk us through this.
Okay, so here what we have is the acquisition module, the acquisition board for the acquisition modules of the 50, 60, 65, and 100 gigahertz oscilloscope. So here we're looking at what I think of as the back side of the board. Distinguishing feature here, we have, you can see there's 4 different sections. Each section is corresponding to one of the input channels. The input signal is coming from the front panel, which isn't shown here, but it's coming straight into the sample and hold hybrids. Coax straight in, so that you don't need to worry about sending that signal, high bandwidth signal, through the board. Instead, you have coax matched as closely as possible straight into the sample and hold.
So this input right here, underneath this is the ASIC designed by LeCroy, which will accept the signal up to 36 gigahertz into the track and holes, which then will split into 2.
Correct. That's the 36 gigahertz monolithic sample and hold chip.
So one other thing before we flip it over is that Alan wanted to point out the way the signals come out. So you were saying about the signal distribution?
Yes. So in the center is the monolithic sample and hold. And what we do is we split that into 16 signals, and 8 go to either side. So we have 2 monolithic ADC circuits, 8 to one side, 8 to the other. And then within each of the MAD chips, we then do digitization of those signals at 5 gigasamples per second each. So effectively we have 2 40 gigasample per second ADCs on each channel that are then interleaved together to get 80 gigasamples per second for the channel.
Yes, and then in fact you may not notice here, if you look closely here on the diagram, you can see you can see 2 of the traces, 2 differential traces here, but if you look at the edge of the connector, you can see the remaining ones come out. And there's more than 8 here, because some of them go, as you mentioned, go to the trigger circuitry, which is in the center, I believe, right here.
Also, this kind of interleaved approach is very common now in the industry. That's how you end up being able to get the very high sample rates, up to 240 gigasamples per second, once we also do the digital bandwidth interleaving.
All right, so we flipped the board over, so tell us what we're looking at.
Okay, so here we're on the other side, and you can see a lot of heat sinks, and we can see for each of the 4 channels, we have, in the center, we have the sample and hold. On either sides is that analog to digital, those analog to digital converter monolithics. And then after we do the analog to digital conversion, we send those samples now to a bank of memory chips. So we designed those chips as well. So we have what we call our MAM chips. So we can see here on these daughter cards, we have individual hybrids now mounted there. So each of those is going to be receiving in some number of samples from those ADC chips, so that we can get a total of about 512 megapoints on each of those channels digitized.
So there's a tremendous amount of data flowing through this board, because you have 40 gigasample per second ADCs here. So there is, on this board alone, 8 40 gigasample per second ADCs, each of them at 8 bits. So you can calculate the amount of data throughput that's on this board. And you can see individual power supplies that provide the appropriate voltages to each individual channel. So this is actually quite a modular design in that sense, because your memories are completely independent, designed to couple with your own ADCs.
Yes.
So this slice is independent from that slice, and the data can be then combined and converted and processed later on.
Correct. Part of the signal flow is to take the signal that's being taken into the sample and hold, and splitting each of those signals and routing that to the trigger chip. So in the center here is our MTT trigger chip, which is now going to look at that signal and then make that decision as to whether or not the scope should trigger. And so there are a lot of different trigger capabilities. You can trigger off of an edge, you can trigger off of a pulse width. And so that's another one of those, another chip that it's designed in-house that's custom and looks to give the oscilloscope the ability to acquire only the signals that you want to see.
And then you were mentioning also that the interface between this acquisition box and ultimately a processing unit and a display is handled through these connectors.
Yes, in the center, those 4 connectors those are receiving all of the data that the MAMs have stored, and then those are then taken through a PCIe bus to the master control module.
And these memories, you were saying that they were coupled to the ADCs at 10 gigasample per second. That's the data flow rate that they're able to accumulate as the scope is running. So each memory module is coupled to its own ADC, like we were saying before, and then all the data is captured at 1/4 of the rate of each of the ADCs ultimately. And then you can collect all of that together and then feed it out through the PCI Express to the main box and ultimately display it on the computer.
Yes.
So now that we've seen this architecture, we now have access to 4 by 36 gigahertz frequency that we can analyze between these 4 channels. So let's go ahead and take a look at how they use this to build a 65 gigahertz oscilloscope now by doing the DBI technology, by attaching by this frequency stitching in order to get the performance from that. So let's go ahead and take a look at the microwave pieces that go on top of this to accomplish that.
Here's the front panel of the LabMaster 10-100zi. So here we have 4 connectors that are what we call the A inputs, and those are for 36 gigahertz operation. We supply crown connectors that connect to give you 2.92 millimeter connections for each of those channels. In the center here we have 2 inputs for the 65 gigahertz operation. Each one of those comes supplied with a V2V adapter so that you can put now in connect a V cable for your signals for frequency content up to 65.
Okay, and then how does the signal flow from those connectors into the instrument?
Okay, so when using it in 36 gigahertz mode, the signals come through a switch and then down into the board, straight into the monolithic sample and holds. For the 65 gigahertz operation, we have our digital bandwidth interleaving capability that we bring to bear. So that's going to take and use 2 36 gigahertz channels and do a frequency interleaving approach to get you a 65 gigahertz result.
So you can see that there's a axis of symmetry in the middle of this. So the bottom half handles one of the 65 gigahertz channel, the top half handles the other 65 gigahertz channel, and then each 65 gigahertz channel is then broken into the frequency interleaving technique that you have in order to feed all the 4 ADCs.
Yes, yes. So let's look at one of those 2 pairs. So coming in to our DBI deck, this component here is receiving the signal from the front panel, and that's now a diplexer that's going to split the signal into high frequency and low frequency components. So the low frequency is going to be from DC to 36 gig, and that now is going to get routed down through switch down to the MSH,
right,
for digitizations. The other path that has the high frequency content. So what we need to do with that now is to send that over to a mixer, which is going to be mixed with a local oscillator that's going to now bring that down. It's going to down convert the signal down to roughly DC, not exactly, but down to DC to 36 gigahertz. And now that's going to get routed now down into the board on the other channel of that pair, and it'll get digitized as well. So now we're digitizing that input signal with 236 gigahertz ADCs. We're going to take the waveforms that we get out of those 236 gigahertz ADCs, and now use digital signal processing to upconvert what we previously had down converted back up to the high frequency band, and then put that together with what we digitized for the DC to 36 gigahertz so that we can recover the waveform of the signal that was input to the scope.
Yes, and you can see that part of the complication of why there are so many components on this board is that it's not just the signal path that you have to take care of, but there are calibration signals coming in and out, which you have to switch in and out depending on what the scope is doing. But ultimately, at the end of the day, the simple message of it would be that the signal comes in, but gets broken into two frequency bands, and then they're fed down into the board from the back connectors we saw earlier. And then all of these things work together. And of course, everything you see here, all the connections and all the switches, all the interfaces are seamless. The user doesn't see any of that. The instrument automatically takes care of switching between all these modes, and the user just has to worry about applying the signal to the instrument.
And there's a lot of art in this. You can get these components and put them together, but that's not going to give you an oscilloscope with the performance that you need. You're needing to look to have good channel matching. You want to have the jitter between channels be as tiny as possible, so that you're looking to match not just path lengths of all of these cables, but also, for instance, to match SN1 or VISWAR for each of these, so that you can really have a tight match, not just between channels in this one acquisition module, but the LabMaster architecture allows you to take many of these acquisition modules and put them together to form an oscilloscope with many channels.
So how many,
get that channel matching.
Yeah, so how many channels at 65 gigahertz can you have currently?
You can have 40 channels at 65 gigahertz as one oscilloscope.
Yes, so you can have 40 channels of 65 gigahertz capture synchronized perfectly together in a massive, massive analysis system that all come together. And because, again, the system is built, the devil is always in the details.
Yes.
There's a lot of stuff that goes, a lot of engineering goes into making this happen. We are simplifying it by just explaining the functionality, but this is really is a work of art.
Right, so when you say the word perfect, that's a word that always makes me shudder a little bit. Nothing's perfect, but yes, as close to perfect as you can get. We have a 10 gigahertz reference clock that's fed to each of these acquisition modules, and so that actually is coming in to the oscilloscope and into this distribution box where we have 4 of these blue cables are now routing that 10 gigahertz clock to each of the components, to the different ADCs, as well as to the I believe to the trigger chip.
So now you can see how this architecture can be used to digitize 65 gigahertz, but now really the exciting and interesting part is to how do we extend that even above that. This is already difficult to synchronize and coordinate, but now to get signals up to 100 gigahertz, you're running into even further problems which don't exist in a coax system like you see here. Now you have to have waveguide components. Now your frequency sampling, the frequency LO signal going into your mixers, as we saw Peter explain, now has to be above 100 gigahertz. And those are a whole different ball game there. So I'm excited to go and take a look at now the same same acquisition board you saw before. We remove all of this and we replace it with a single 100 gigahertz channel that does a ×3 frequency combining technique. And let's go and take a look at that. And here we go. This is where all the magic happens with the 100 gigahertz dBi architecture. And what we've done is that we've also placed a little block diagram here just to remind you of what it looks like. There's nothing under the paper, so you're not missing out on anything. This is a really early model, so it has some of the microwave switches here that are not installed. But Alan's going to walk us through from the 100 gigahertz input, which is a 1 millimeter connector, and then we're going to go from there and think about how the different bands are architectured, just like we have the block diagram here. And you can see that, and one of the reasons this may look a little bit simpler at the beginning is because there's only one channel at 100 gigahertz. The previous system we were looking at had 2 channels at 65 gigahertz, so therefore they had 2 of the half. So if you wanted to have 2 channels at 100 gigahertz, you'd have to replicate this again, of course, and you'd have to have a whole different acquisition board. So go ahead and tell us a little bit about how this works.
Sure. So this is what we refer to as a dBi tripler, where the 65 gigahertz use 2 36 gigahertz channels. This one's going to use 3 36 gigahertz channels in its digitization, and using dBi to get to 100 gigahertz. So the signal comes in over here on the right side of the board, where this black cap is. That's our 1 millimeter connector, and that's coming into one of 2 diplexers. That's going to split between the high frequency band and the middle and low. So the high frequency band then goes into some stages for amplification and makes its way over to a mixer, where it's going to be mixed with a 102 gigahertz local oscillator. And the output of that now is going to get routed down into one of the 36 gigahertz channels for digitization. From the other side of this first diplexer, we're going into now a second diplexer, which is going to split off the low frequency content from 0 to 35 gigahertz to and as well as the mid-frequency content from 35 to 66.5. So the low frequency is taken out from where that red cap is and routed over to a switch, and then down into the board, into the monolithic sample and hold chip for digitization.
And right now that's not there.
Right.
Just to remind everyone that this path that's going into ADC, because it's an early model, that path is not there, but eventually that would go back down to one of the digitizing channels we saw before.
Right, right. So you can see a cutout here where one of those switches would be, and there's another cutout under the paper for another one of those switches to route the signal down into the board, into the acquisition board. So from the second diplexer, we're taking that output, going through this RF module, and then into a mixer stage where we're going to mix that signal, which now comes in with 35 to 66.5 gigahertz frequency content. We're going to mix that now with a 67.5 gigahertz local oscillator. And now we're going to get 1 to 32.5 gigahertz frequency content coming out of that mixer stage. And then now that's going to get routed down through a switch down to the acquisition board into another one of the 36 gigahertz channels. So we have now 3 36 gigahertz channels being digitized, one doing low frequency, one doing mid frequency, one doing high frequency. And now those 3 36 gigahertz digitizations are going to be taken and processed. The mid frequency is going to go through DSP that's going to upconvert to bring back that to the 35 to 66.5 gigahertz band. And for the 36 gigahertz digitization for the high frequency band, we're going to upconvert that in software to the 66.5 to 100. And then we have these 3 data streams that we're going to now put back together with DSP to come out with our final waveform, which will have that 100 gigahertz content.
Yeah, so just to recap everything that you said here, so if you think about it in terms of signal path, 100 gigahertz signal comes in here, goes through here. This is the 66.5 to 100 gigahertz path, so the signal comes through here, down converted. Here's our first output, goes to be digitized. The signal then is split again, goes through here, mixes down. Here's our second output, that's from 33 to 66.5, and then our first 0 to 33.5 gigahertz, so go in that direction. Another couple of interesting things to note here is that, again, remember, based on also what Peter said, that the sampling frequency of the mixer in the high band, the highest band, is at 101 gigahertz. So you can see they've chosen to connect those two pieces together with a waveguide as opposed to with a coax, because it doesn't make any sense anymore to use coax at those frequencies. And there's also a whole bunch of synchronization clocks and so on that Peter mentioned that are present in this without going into too much detail. But yeah, there's quite a bit of stuff happening here. But the really nice thing about it is that if you think about it in terms of architecturally, they have built all these systems on the initial digitizing board. So they just reuse the ADCs they've designed, and they built continuously these frequency interleaving techniques in order to get higher and higher digitization bandwidth. All right, and here's the part I'm sure you've all been waiting for. So here we have a full system put together, as well as some optical tests in order for us to generate very high frequency signals. But before we go through there, just a quick overview. Here at the bottom, we have the 100 gigahertz scope, as we saw the internal construction. So the board that you were looking at last is essentially in this direction. Here's the 1mm front-end connector. So that's what we're looking at. So this would be the 10-100zi module, and with all the high-end sampling modules from LeCroy, they have a LabMaster component here, which then is a master control module which collects all the data coming from the sampling modules at the bottom, and of course has a display on it which will take care of processing and displaying and all the math functions, all the advanced systems that they have there. And we'll show you the back of this and how these things are synchronized together as well. So I'm going to pass it again to Alan. Describe to us what we're looking at.
Sure. So what we have here is our LabMaster 10-100zi oscilloscope put together that's the top and the bottom components. And in the middle, we also have an instrument here, which is a coherent optical receiver from our partner Coherence Solutions. We partnered with them to use the LabMaster as an optical modulation analyzer. We're not going to do optical modulation analysis today, but we're going to use their instruments to do an experiment where we're going to beat some lasers against each other to look at a tone. So the LabMaster is an important piece of equipment, and we have a lot of customers in the optical community. So we thought we'd do an experiment today using optics. So we have here this yellow fiber. So we have an optical fiber that's bringing a signal into the coherent optical receiver. The receiver is going to demodulate that signal. It has a local oscillator that is being looped back to be used, and we're going to take the output of that into the oscilloscope. Right now we can see that our laser is off. We're starting off here with just sort of a noise trace, and what we're going to do is we're going to get the instrument up and running in a minute. On the right side.
So sorry, Alan. So the idea is to take a laser here that is sitting at 194 terahertz, and you're going to generate another laser for us from another IQ transmitter that has a frequency of up to 100 gigahertz apart from this laser, and the product of those two, mixing product of those two, is going to give you an analog electronic signal, which we can then stress the scope up to 100 gigahertz, and that's basically what we're trying to build here.
Yes, correct. Yes. So on the right over here, we have from Coherence Solutions, we have their complex modulation transmitter model IQ transmitter, and so this instrument is designed to be able to output a dual polarization signal. Right now, we're going to use it in the mode where we're simply taking the internal local oscillator out. Later, we're going to use it in a different way. But right now, we're going to take a 194.05 terahertz optical signal. We're going to bring that through and into our coherent optical receiver, where, as Shahriar described, we're going to beat that laser of 194.05 terahertz against 194 roughly, and look to see the 50 gigahertz sine wave that will come out of that mixer.
Okay. So here we're looking at the back of the acquisition mainframe as well as the LabMaster. So here you can see Alan's going to explain to us how it is possible for them to have so many channels at such a high bandwidth all synchronized together, the way they connect to each other via a bus at the back and all the synchronization. So tell us, Alan.
Okay, so we have here the back of the master control module, the LabMaster MCM-ZI, and at the bottom is the acquisition module, the LabMaster 100zi. And so this is a modular system, and you can see how they're connected. So at the top here, we have the 10 gigahertz clock outputs. So there are five of them, and we're using one at the moment connected to the AC module. So this is using our channel sync architecture to be able to then keep multiple acquisition modules locked together using a common time base, 10 gigahertz. Conventional instruments use 10 megahertz or 100 megahertz to sync. You can't accomplish the close channel matching that we get with such a reference clock. So we use the 10 gigahertz clock distribution. Here we also have a PCIe cable using one for each of the module that you can attach for syncing for trigger signals and such. And then we have the data cable, which is also PCIe, but more lanes than the sync cable. So they come into the AC module. So we have our 3 cables connected. This system supports connecting up to 5 acquisition modules. So you can connect 500 gigahertz scopes. You could connect other scopes in the series. So you could have a system with, let's say, 20 36 gigahertz channels, with 10 65 gigahertz channels, 5 100 gigahertz channels. The architecture supports even more acquisition modules. So we can use a separate hub, a channel sync hub we call it, to be able to route these signals to up to 20 acquisition modules. And you can get a system with 80 36 gigahertz channels, 40 65 gigahertz channels, or 20 100 gigahertz channels. So that would be a powerful system indeed.
So that would be, in that configuration, you would have 20 240 gigasample per second 8-bit systems, right?
Yes.
Yeah, just put
Yes.
to multiply those numbers, and that's the throughput of the whole system. That's how many bits are generated, computed,
Right.
and eventually ultimately displayed. It's really amazing.
Right. And any two of those channels are locked together, and if you looked at what the jitter is between any of those two channels, it's going to be nothing more than perhaps 150 femtoseconds.
So your clocking scheme noise floor is about 100 to 150 femtoseconds in total.
That's the matching, the channel.
Oh, the
channel
matching. I see.
match.
Do you have a
Right.
specification on the 10 gigahertz clocking jitter noise floor?
Well, the sample clock itself is about 50.
50 femtoseconds, yes. And you have to have that, of course, otherwise you will never meet the enough of the system
Right,
altogether.
Okay, so let's get this up and running. So what I'm going to do now, I'm going to turn on the lasers. So hit our buttons here for laser on.
Right? So these
And-
lasers take a little bit of time to start up, but you can see here, let me focus on this one, there it is. So this one's cranking up to about 15 dBm, 194.5 terahertz. This one is cranking up also to about 15 dBm, 194 gigahertz. So the difference should be a 50 gigahertz signal. Let's take a look.
So that's the next thing we're going to do. We're going to analyze this. So here we see we have a signal on the screen. So let's just talk about what we can see. So right now we have channel 3 turned on, 80 millivolts per division. That's the signal that you're seeing. Over here we can see in our what we call our time-based dialog that we have a signal that's acquired. It's 480 samples, and it's acquired at 240 gigasamples per second. So 240 billion samples per second. And that is at a time base of 200 picoseconds per division. And here we have the trigger set up to just to auto trigger looking for an edge on channel 3. So the oscilloscope can be used in a few different modes. We can use that 100 gigahertz input, that's what we're doing now, but you can also use it in the mode where you're going to use a 65 gigahertz channel, same input, and then use two 36 gigahertz channels. Or we could go and just, if I click this button, we would just use it as a 4 channels at 36 gig.
So it's very nice that buying the 100 gigahertz option still gives you all the frequency bands that you would want to work at. So if you want to simultaneously have two 36 gigahertz and a 65 gigahertz, it's still possible. The microwave pads support that configuration just as well as the other model that you have. Okay? So just one other thing that I wanted to also point out is that what you're looking at here, and again correct me, Alan, these two coherent lasers are unlocked from each other.
Correct.
So as a result, you have a phase that is not locked between this laser and that laser. As a result, the frequency we are seeing is going to drift, and the amplitude is going to drift because that's just the nature of the unlocked lasers. The variation that you see here and the drift you see here is not from the oscilloscope, it's from the lasers. In fact, because you have such a high sampling rate, you can actually characterize that drift if you wanted to and find out how fast the lasers drift with respect to each other. And if you're working on things like optical phase lock loops and things like that, a system like this at very, very high sampling can allow you to lock lasers that can be 100 gigahertz apart, which normally would be invisible to you.
Yeah, so we can actually look at that drift in phase or in frequency. We could track that within an acquisition, or we could see over longer time periods. We could see what the trend is, if there's low frequency jitter or wander. So let's zoom in a little bit on this. We're gonna get a better volts per division so that we can fill up our grid vertically.
There you go.
So I'm going to click it. I'm going to go to a variable gain so we can just a little bit more.
You can hear the various calibration routines internally. There we go.
Okay.
So now it's filling. So now it's at 30 millivolts per division approximately.
So I could hit the zoom button. We could see a zoom of that.
Yeah.
So one thing we could do, we could add some sin x over x interpolation. So I'm going to go to the channel 3 dialog to our pre-processing, and we can add sin x over x. So looks like I've chosen a volts per division where we're still overflowing occasionally. due to that variation. So I'm just going to go back this off a little bit so that we're not overflowing.
Yeah.
Okay. All right, so here we have a short waveform. We're seeing that we've got sine waves. So let's see how we can measure the frequency of that. So I'm going to go up here and I'm going to turn on my measurements, and I'm going to go to standard horizontal. And this is going to put up a bank of measurements: rise time, fall time, period, frequency. So here we have a frequency column that's showing us the value of the very last cycle and then the mean. And this is what we can look at. This is the average frequency that's been measured over all of the cycles that have been accumulating. So it's accumulating data. We got a 50.05, et cetera, gigahertz sine wave.
Perfect.
All right, so the next thing you might be interested in investigating is the frequency content. So we could take this waveform, we could do a Fourier transform of it. So I'm going to go do that now. So I'm going to go to our math button here. One way to put up a math function on the screen. So here, since I actually set this up before, the category frequency analysis is there, and I'm going to choose FFT. And looks like we already have it selected for F1, FFT. So we're going to use that. Close that up. And so now we have math function F1 set up to be the FFT of C3. So we could look to put a few more grids on the screen if we want. So now we have our waveform, a zoom, and we have an FFT. And so here, given the time base that we've selected, we have some frequency spacing in our FFT. We have some span based on the sample rate.
Yeah, so actually it's interesting because this is 110 gigahertz, correct? Right now.
Yes.
Yeah, so that little area they're looking at, and this brick wall filter is the DSP filter at 100 gigahertz that you have selected because the sampling rate is 240, so FFT will lead to a very large span. So
right.
I guess you can go ahead and zoom in by changing the time base.
Yeah, so the reason why we have that span as well is because we're doing sin x over x interpolation.
Yes, so you get lots more bandwidth. Yeah.
That's giving us more frequency. So I can go in and I can change, for F1, I can go and I can change the scale, for instance, instead of being 120 gigahertz per second, let's choose 12, and then we can put the center here at 60 gig, and so here we have now sort of a better scaling. So let's go and now actually acquire a longer waveform so we can get some better resolution in this spectrum. So I'm going to go here. And of course, we could do everything from the user interface, but there's certain functions that I go straight to the front panel. Some things I like to go to the user interface.
Yes.
So, but let's go to a longer time base. So here I'm cranking it up slowly, and here we can see that we have a faster, I need to say, an FFT with better frequency resolution.
So you can see that tone. This tone will then correspond to our 50 gigahertz beating of the two lasers, and you can see that it ever so slightly wiggles back and forth because the two lasers are not quite locked to each other. So you can see the variation there.
So we could also get a measurement of that frequency. I could select my to change one of my measurements. Right now we're set for what's called standard horizontal. Instead we could look to use what's called my measure. But first we could do a quick setup. We could get all of these from the standard horizontal. So that's what we had before, but now I can set up P9, and let's take the source, math function F1, measure. And so here we have our selector for all the different measurements that we can do. So here we see there's a lot of measurements built in.
There's a really extensive set of advanced mathematical functions built into all of the LeCroy LabMaster units, and you can use maths as a function of math as inputs to other functions and create really complex live analysis.
All right, so we're going to choose X at max, and we're going to choose to find the maxima, and there we go. So now here we have X at max, and it's finding our 50 gigahertz peak. We could then as we discussed, we could look to show how that's varying in time. We have trend and track kind of functions that I could put up here. So I could hit trend, and we can use math function F2 to do a trend. Oh, so here you can see a trend is
being built up slowly.
So if this is drifting in any predictable way, or if it's got some characteristic of these lasers where if there's phase noise that can be that correlates with some other type of behavior, then you could use this waveform to learn more about the problems in your system and how to and so that you can debug them.
So this would be an interesting point to try and change the frequency or the wavelength of the second laser, and then we should see the peak here at the FFT move and also the trend move as the frequency shifts. So let's maybe go ahead and try that if you want. Right now we are at, as I mentioned before, here we're sitting at 194.05. So let's try, let's go another 25 gigahertz. Let's go 194.075. That would then generate a 75 gigahertz analog tone in the electrical domain, which we should be able to capture again with the oscilloscope.
Okay, so I'm going to change it to 175. The laser turns off, turns back on. Now it's ramping up in power. And we can see on the scope that effect. We have now a peak that is it's showing up here. And we have here now a big change now in our trend plot. So our trend now shows that we have changed our frequency from one level to another. And for instance, you could bring up, for instance, a cursor and look to apply the cursor to that waveform and see what those values are.
So you can actually see an interesting effect here where here in the trend you can see that the impact of the laser being turned off and turned back on and so on, where you can trace that exactly, and then by putting a cursor on it you can then read each individual point. I assume.
So here we have at this point that was where we were at 50 gig, and then over on this side now we're up at 75.
Yes.
So now our measurement here is still where those measurements weren't cleared. So this is not showing 75 for the average. It's showing it for the value, as you can see right here. But here it's still building statistics. So we could clear our sweeps, and we could see that this now would be a more solid 75.
Yes, that's the average basically. So if you press clear screen right now, you will.
Well, let's clear. We don't want to clear the math sweeps.
Yes.
We'll just clear the measurements.
Okay, perfect.
There we go. So
that's the other nice thing is you can independently clear statistics for various components that are being displayed on the screen without clearing other things.
Right. So this clear sweeps button on the front panel would clear out all of the measurements. But here now, this is how you can clear out just the measurement system. That clear sweeps clears out not just measurements, but the math functions, clears out all the processing.
All right, well, let's push it further. Well, let's try go all the way to 100. Let's see world's fastest 100 gigahertz true digitization of a signal, and that at this point no one else in the industry is able to do. Here we go. So Alan is changing it. So if you take a look here, now we're sitting at 194.1 terahertz. And that would be 100 gigahertz, and then we can go ahead and see the signal. I guess you can change the vertical scaling now in order to have even more resolution. But take a look at this.
So here we have our
laser tone.
Peak. Since we have now we're at 100 gigahertz, we have some attenuation. And part of that is just due to the cabling. This is coming out with out of a K connector. So this isn't rated to go out to 100 gigahertz. The receiver goes out to about 70.
Yes, yeah, exactly. I want to make sure that you don't mistake this attenuation with the attenuation of the instrument itself. This is an attenuation of the cable plus the optical detector when you're beating two lasers together. That detector is not designed to put out a 100 gigahertz signal. As a result, its frequency response is rather limited. But the scopes, of course, has a flat frequency response after extensive calibration that is done. So that should be not a problem. But one thing I want to, again, point out here, this is 10 millivolt per division, correct, Alan?
Correct, yes.
So this is a 10 millivolt per division signal, 100 gigahertz being sampled and digitized. So it's not like we're dealing with, 1 volt peak-to-peak signal here, which you may assume, digitizing would be a little bit easier, but it's a 10 millivolt peak-to-peak. So very, very small signal, true digitization, 100 gigahertz. Very impressive.
Yeah, I'm going to also adjust our zoom here for our zoom trace here. That's the offset. Wrong knob. Here's right now. Here we go.
There you go.
So there's a zoom in of our of the source. You can see that thin blue trace, which is now being zoomed in.
Yes.
So while we're looking at now 5 nanoseconds per division for the full sweep in channel 3, our zoom trace is showing 20 picoseconds per division.
Yes, and again, the amplitude variation and phase deviation you see here is again due to the lasers being incoherent to each other, but you can see we have a true digitization of 100 gigahertz of signal. I would imagine for the first time. I'm sure you've shown this before, but definitely a first time on the signal path. 100 gigahertz digitized signal. Pretty incredible. So something that is also interesting to try to really show not just the capability of the scope to capture signals that are very high in frequency, up to 100 gigahertz, but also show some correlation between various frequencies. So here we are looking at what we had before. We have a single tone. We are capturing right here that this tone has 90 gigahertz as before, but now what we're going to do is we're going to also apply an RF signal to the modulation port of the IQ modulator, but only on the I side or on the Q side, and this will allow us to create a double sideband, which is equivalent to an AM modulation in the frequency domain. So if I were to apply, for example, a 2 gigahertz signal to the IQ modulator, I will see 2 tones on the sides. There you go. Alan just turned it on. Now we have 2 extra tones, and we're capturing this. Remember, this is 90 gigahertz. This is 88 gigahertz. That's 92 gigahertz. But another thing that I wanted to say to convince you that this shift in frequency is not because of the instrument, but because the lasers are unlocked, is that you can see these 3 tones moving together, and that's because the stability of the modulation signal, the 2 gigahertz RF you're applying, is much more than the coherence between the 2 lasers. So you can see that they are together. So Alan's going to explain to us a little bit now how we can measure the difference between these frequencies and show that it is a stable frequency measurement.
Okay, so let's turn on those measurements, the exit max measurements. So I'm going to just turn my measure table back on, and you see here I have some measurements already set up. So here I have in parameter 1 exit max, and here my source of the exit max measurement is Z1, the zoom trace that we're using, and I've set up some gates so that it finds the peak, and so I have P2 set up to be to look for a second peak, and we could do this for the third one as well, but to keep it simple we'll start with those 2. Then in P3, parameter number 3, I have that set as math on parameters, and that's now taking the difference of the measurements of P2 minus P1, and so here we can see that we've come up with a mean value of something very close to 2, 1.9997.
Yeah, so just remember exactly what we're measuring here. This 2 gigahertz signal is the difference between a signal at 92 gigahertz and a signal at 90 gigahertz, or 88 gigahertz and 90 gigahertz, and this is live digitization. I know that we may have gotten used to seeing these signals, and you may think that, you know, this is not a spectrum analysis, this is an oscilloscope. It's capturing from DC all the way to 100 at the same time, and we're looking at 2 tones very close together up at 90 gigahertz, and you can see that. So this 2 gigahertz signal here matches our synthesizer RF input right there, which yeah, there you go. If you push that little piece of fiber connection to the side, you can see there it is, just blocking the number. There it is.
There we go.
There you go. So now you can see that's a 2 gigahertz signal that we're feeding into the IQ modulator, and the small amplitude is only 100 millivolts, and then you can see that we have no problem digitizing the entire spectrum and measuring the difference in frequency, and you can do, of course, all kind of fancy analysis on it.
So one thing we can also now do is we could also increase the amount of time that we're zoomed in on. So here you can see that modulation pattern.
Yes, remember that if you feed a signal to only one side of an IQ modulator, you get a double sideband signal on each side. It's equivalent to an AM modulation, which is what we're looking at, and you also have the carrier here in the middle, which is the result of the 2 LO signals beating together. So this is a very clear example of capturing small deviations in frequency by digitizing the entire signal. Now you can think about this as being a broadband optical signal, which you can, of course, then demodulate and post-process, and there have been record-breaking optical transmissions, for example, from Bell Labs using this oscilloscope for the first time, showing really high data rate dual polarization optical systems using the similar measurements. Now the next thing I want to do is to set up another experiment quickly, just so we can see some really, really fine pulses that we can capture because of the high sampling rate of the oscilloscope. Alright, so as our last experiment, what we're doing here is we're going to try and capture a very, very narrow pulse coming from a femtosecond pulse laser, which is a unit you see all the way over there. So the idea is that we would generate an extremely narrow optical pulse here. That optical pulse is fed to a photodetector with a really, really high bandwidth in the order of 80 or 90 gigahertz or so, and that will get converted into an electrical pulse. That electrical pulse is fed into the 100 gigahertz sampler of the scope, and we should be able to capture that and look at that pulse. This is a particularly difficult measurement to do because the pulses are really, really narrow, and in order to capture and trigger on them, there's a trick you can play where you can actually trigger off of one of the other channels of the oscilloscope with the synchronization signal that's coming from the pulse generator itself, and then you correlate that and you can do some computation in order to generate the pulse. So Alan's going to explain to us exactly what it is that we're looking at.
All right, so we have a laser from Calmar Opticon. It's something like 100 femtosecond. It's coming through an optical attenuator, and then what's hiding behind here is just a joint, a union, and then into the photodetector, and then into the 100 gigahertz channel. Then we're using a pro power bus here with a sort of just a specially designed 2-volt supply to bias the photodetector. So we have the oscilloscope set up. Here we're acquiring our waveform, and as Shahriar said, this is an extremely narrow pulse, and so we're looking to optimize the scope setup so that we can get this pulse centered on the screen using an external trigger signal as well as some software-assisted triggering and some other setups as well. So here we have our pulse, and now we're doing some analysis on it. So in math function F1, we have that set up for what's called our p-trace mean. So what this is doing in F1, it's building an average of, or a persistence map using channel 3 as its input, and then it's outputting a waveform that is the mean value through that persistence map. So it's finding where that signal is in the persistence map. Then we take that and we're zooming here on the lower right, we're zooming in on that bright yellow section of math function F1 of the p-trace mean. So now here we have the best representation that we can show you of the measurement of this laser pulse. So the next step is to do some analysis of it to see, to quantify it. So over here in our measurement table, we have it set up for a few measurements. Here we have it set P3 set up for the width at level measurement. So the level is currently set to 50% level, and here we have a marker that shows that. And so we're recording a value of 7.786.
Yes, that's the width of the pulse at a 50% level.
Right. Then we're taking this and now looking to understand what the rise time is of the integral or the integrated pulse. So that would give us our step. So here we have a step that's the integral of our pulse. And when we look to make a rise time measurement on that pulse, rise time 2080, rise time 1090, we measure 4.2 picoseconds for 2080 rise and 5.9 picoseconds for 1090. Extremely fast rise times that you can only measure if you're using 100 gigahertz,
yes.
And 100 gigahertz oscilloscope as we're doing here.
Yes, and it's interesting to note at the same time as these pulses, while being extremely narrow in width, are also really infrequent. Mm-hmm. They are 100 nanoseconds apart. So this pulse here, as narrow as it is, the next pulse that's coming from the laser is 100 nanoseconds after. It's almost a lifetime later compared to the width of the pulse itself.
Right.
And the amount of energy that the scope is capturing in this pulse is absolutely tiny. And so on top of that, you have to, of course, trigger it, as Anne explained, with the tricks that they're playing to do that. And when you're integrated, you can then measure the total amount of energy in that pulse and so on. And the limitation in this pulse here is, in fact, essentially primarily because of the detector itself, because the detector doesn't have enough bandwidth to support. So what you can do with this mechanism is to actually measure the bandwidth of a really, really fast photodetector by measuring the pulse width, because you know the scope's 100 gigahertz bandwidth is not your limitation in this case. And there is no cabling, so the calibration plane of the scope is at the edge of this connector. So whatever you see is now the bandwidth of the detector itself. Yeah, so this is I think this is a pretty good and conclusive test to do to show some of the more advanced capabilities of the scope.
Right. So with the 100 gigahertz oscilloscope, we've got an oscilloscope now with a bandwidth that really is wide enough that oscilloscope bandwidth isn't a limiting factor now for making these measurements, and either for fast pulse measurements of this type or for doing work in other optical areas like coherent optical, looking to understand, companies looking to measure very fast baud rates and forming constellations at 80 and 160 gigabaud. That's key players, key customers for this product.
Alright, so we had a good in-depth look at LeCroy's 100 gigahertz, 240 gigasample per second 100zi series oscilloscopes, and you saw the manufacturing, the calibration, and really the building internals and the block diagrams of how it works, and some pretty impressive measurements. So I'm really happy to have been able to come here and take a look at this by myself. And if you're interested in using something like this for your applications, there is a dedicated email address which is 100 gigahertz, that's 100GHz at teledynelecroy.com, which you can send an email. They'd be happy to get you in touch with one of these and send you a demo even, and so you can try it out for yourself. And I want to thank Alan again so much for having me over.
Thank you.
And being able to take a look at this incredible instrument, and hopefully this will spark some future collaborations between LeCroy and the Signal Pad, and pretty exciting. So until next time.
Well, there you have it, a close look at Teledyne LeCroy's 100 gigahertz scope. I'm sure you were just as excited as I was when I was seeing this instrument actually at play. And there's a lot of other experiments, of course, you can do. We only scratched the surface, but as you can imagine, this instrument is intended for a very, very specific application, because even fiber optics barely have bandwidths that can reach the bandwidth of this oscilloscope. It's really intended for next generation optical or even wireless communication, but it has some really unique and interesting features, which I'm discussing with Teledyne LeCroy separately for some research applications and so on, which would be very interesting. So I really highly recommend that you go and take a look at some of their material that's available on their website. They have a publication that shows how this technique works. The person who's invented this technique is an IEEE fellow, so he's got a lot of experience doing these type of things. So go ahead and take a look at it. And next we're going to go walk through the factory. You're going to see the different stations, and this is not just a factory that assembles, of course, the 100G scope. This assembles the entire lineup of all the Teledyne LeCroy's oscilloscopes, so it should be pretty interesting for you guys to see how a system like that is put together. They're very neat, very organized, as they have to be in order to create these instruments with the grade that they do. So let's go take a look at the factory tour.
Hi, my name's Tyler Cox. I'm the Vice President of Manufacturing Operations here at Teledyne LeCroy in Chestnut Ridge, New York. And we're going to take a quick tour through our facility.
Thank you.
As you can see as we walk through the facility, this whole manufacturing floor is actually set up on a cell-based process, meaning depending on the kind of product that we're building, the whole operation is done within one particular cell. And so as we walk around, we're really divided up by bandwidths, because the equipment and the processes and the know-how that are required to build a 4 gigahertz scope are different than the processes and equipment and calibration that you have to do a 40 gigahertz scope. So as we walk through, we'll see we're really divided up into what we call a mid-bandwidth products, meaning things that range really from 300 megahertz up to 4 gigahertz, a high bandwidth cell that would really do from about 4 gigahertz up to 20 to 30 gigahertz. And then we have one tucked away in the corner called an ultra high bandwidth cell. And this is really where those very high-end 65 gigahertz, 100 gigahertz kind of products are going to get put together.
Good morning. My name is Mark DeVries. I manage quality assurance and manufacturing at Teledyne LeCroy in Chestnut Ridge, New York. I'm going to walk you through the assembly and test of the product which we call HDO 4000 6000 oscilloscope. The process starts with acquisition assembly, which is what we have here. This was an acquisition card, and it's as delivered from our subcontractor. All the components are soldered onto the board. We have our front end, which is under this shield here, feeds into analog to digital converters, and then memory modules. This chip here, which is green, is a custom LeCroy HTT, which is our timing and trigger chip. At this station, which is an assembly station, we will glue on the heat sinks in the appropriate step, put on the appropriate cables, and now this particular card is at its higher level assembly that can now get moved to test. On these trays, we have fully assembled acquisition cards that are now ready for programming and testing, which happens here. Our first station, which takes about 3 minutes, is what we call programming. You're going to hit the button, Robert? So Robert, a senior test technician, runs the program, and it's a multitasking time. So while he's doing tests, he can also do programming. The card is now actually being programmed based off of the computer, and when it's done with programming, we can move to test. Let me slide over to test, Robert. Yep. Test happens here. This is a fully custom test fixture for this particular card. It rotates, so if necessary, we can get to the back of the card as well as the front of the card. The cooling also simulates the cooling when it's in the box, so that when we tweak this, it's comparable environment when it's in the box, because heat matters a lot to our front ends and acquisition systems.
So this is a complete thermal simulation of the final box, basically.
It's real close.
Yes.
It's to the point that when we make adjustments here, they're acceptable when it's in the final scope. This station here, we assembled the back box for the HDO 4K and 6K line. The manufacturing work is done via what we call a do sheet, which is what we have here. It's a sheet we fill out for every back box that we make. In the back box, we're taking sheet metal, we're putting the motherboard, the processor in the motherboard, the fans, the power supply into the back box chassis. All the tools are calibrated for torque specifications, and all the hardware is available at the point of use for Christina to do this complete job here. Cables are on the top shelf, fans to the left, all the tools here. When Christina is done, she'll sign off her do sheet and put it on the shelf here to the right. So here we have two examples of completed back boxes. We have the motherboard, we have the processor, we have memory in the motherboard, we have our AC to DC power supply underneath this fan duct with its fan here, and our AC inlet board, which distributes the power. This back box, at the next step, will get married with the acquisition card in what we call the front box, and we will then have a full-up oscilloscope that we can power on. This station here we call front frame and naked assembly. It takes about 25 minutes. Ankia is starting off building the front frame. The front frame starts off with a piece of sheet metal that we mount the TFT and touchscreen to, and Ankia is doing that now. So this is actually a simulation that I'm asking Ankia to do for the purpose of the video. This would get screwed in, torqued in, and so forth. At this point, let's just lay the back box over the top, Ankia, after one screw, so we can get it on video.
Okay.
Just lay the back box over the top. In total, this process would take 25 minutes, but for the purpose of video, we're just simulating the construction so we can kind of see how it goes together. Front frame is completed, acquisition card gets put in, back box would then get integrated onto the front frame, similar to what Anki is doing here. Goes together quite nicely. The front box and back box get cabled together. We put cables to the acquisition card. It all gets screwed together. It all gets torqued together. Ankia finishes her torquing of all the sheet metal, and we're done with front frame and naked assembly. We call it a naked assembly because it doesn't have its final plastics, its final close. So this is a naked box, and here, if we move forward, here's what we call our power on test. So we've taken the completed assembly, we power it on for the first time, and again, this is an example of what we call naked assembly because it doesn't have its final plastics. We can power this up like an oscilloscope, which is what we're doing here. We do Windows updates. We check for some for some testing via our traveler to make sure we are working like a full-up oscilloscope. The turn-on rate here is almost close to 100%. And after power up and Windows updates, the next step, this would go to CalSoft, which is short for calibration software, is our full-up functional test and calibration. Next step after power on would be high pot, and that happens here. This is a safety test since we're putting line voltage into the box. This makes sure there's no shorts between the power supply and the sheet metal, so the customer is ultimately safe. There is no ability for line voltage, 110 or 220 volts, to leak or get to the metal to zap a customer. After high pot, we go to CalSoft. CalSoft is a fully automated test and calibration sequence. We have 8 CalSoft stations, and each CalSoft station can test any of our mid-bandwidth scopes. Here we have a Wavesurfer 1000, Wavesurfer 10 scope. Here we have a WaveRunner 620zi, and here we have an HDO 6104. The 6104 is a 1 gigahertz 4-channel scope. It has finished its CalSoft. Yes?
Well, yeah, this one's a golden scope.
Okay. It's finished its CalSoft. At this point, the technician, Joe, would print out its calibration certificate, put it in the folder, and move it to its next step.
So, for example, for the 6000 series, how long does like full calibration take usually?
About 2 hours.
2 hours.
You have a technician here that's constantly able to, check up on it.
So one operator can run all 8 stations, and on average, assuming we have a unit that passes, it's about 2 hours on the station. They are automated. We have Pickering switch boxes. Our turn-on rate is north of 98% here. So on the mid-bandwidth product, we have 98 out of 100 that pass CalSoft, and we're quite proud of that. If a unit doesn't pass, we would typically take the acquisition card out and figure that one out. But very, very high turn-on rate here. After CalSoft, the scope is at its highest common denominator. It can then go into finished goods to be married up with its ultimate sales order, where we do a configure to order. Oscilloscopes nowadays have so many software packages that are available. The configure to order process is loading the customer required software packages that they purchased, picking probes from inventory, testing them on the scope that they're going to ship with, final quality control, turn it on, store a file to memory, recall it from memory, touch the touchscreen, turn the knobs, because our automated test system is exactly that. It's an automated test system. And while we sell into test environments, automated test environments, the primary user of our oscilloscope is an electrical engineer doing debug or research and development. So they will be using the touchscreen, turning the knobs. So we make sure we do that with a human before we ship it to the end user. This workstation is what we call skinning. Skinning is applying the final customer plastics, as we see here. We have our front bezel with our encoders and encoder board. We have our back bucket with serial number and trim ring and feet. This process takes about 30 minutes to get everything bundled up, and at this point, when we're done, the scope is at its highest common denominator. It's a full-up scope that if there are no additional options, it'll be shippable to the customer. This step is what we call lockup. Lockup is final quality control and configure to order. John, who's doing lockup, has actually been working at LeCroy 19 years, is actually doing lockup on one of our WaveMaster scopes. At this particular step, he puts on the final plastics. We only put the final plastics on here because we do have the option to install increased processor memory if the customer wants, so the plastics are only put on at the very end. Lockup is for WaveMaster is applying the plastics. John will also take the sales order and configure to order. We have about 150 different software options where John can load the software into the oscilloscope. He will power up the scope, use it like the customer, turn the knobs, adjust, work the touchscreen. Even at a lockup, we have a lockup check sheet. This particular one is Rev D, and it lists the 75 steps we're going to go through to lock up this unit. Again, final quality control and configure to order. When John is done, this unit will be put in its box and shipped to the customer with all the probes, accessories, manuals, power cords, everything it needs. So a very key step, and we have our most senior people doing this job because it is, again, the final person to touch the oscilloscope before we ship it to the customer. So what we see here is an acquisition system comparable to a 36 to 100 gigahertz scope mounted in its chassis. The green printed circuit board is mounted to a matrix similar to this. That's a quite large board. As soon as they come in the door, we mount it to this frame. It's a quality assurance step. We don't want the board to bend or be flexed in any way, because there's greater than 15,000 components on there, greater than 30,000 solder joints. Under each of the large heat sinks, we have a LeCroy custom analog to digital converter. And these cards are custom memory that LeCroy is designed to work within our acquisition system. A very complex board, but this comparable acquisition card can get used between 36 and 100 gigahertz in this type of chassis. Clearly, to get to 100 gigahertz, we do some additional things though. Is our the top end of our 65 gigahertz oscilloscope, our 65 gigahertz acquisition system. The acquisition card is on the bottom, and on top here we actually have our microwave device, which is essentially a bandwidth doubler. It takes our 36 gig architecture and doubles it up to 65 gigahertz. It's all piped with rigid and semi-rigid cables. Very complex, but very accurate and very high tech. So where we are now is what we call high bandwidth and ultra high bandwidth CalSoft. We saw mid bandwidth CalSoft earlier. Here the station is a little bit larger. We have 1, 2, 3, 4, 5, 6. We have 8 CalSoft stations for high bandwidth and ultra high bandwidth. Here we calibrate and do performance verification of our WavePro, WaveMaster, and LabMaster products. At these stations, we can calibrate between 4 and 65 gigahertz. They are all computer controlled, and we have one operator who manages multiple stations.
So you were mentioning that you calibrate up to 65 gigahertz here, and then for the 100G scopes, you have to send them somewhere else?
So on this particular station here, we can calibrate our slaves that up to 65 gigahertz. When we need to go to 100 gigahertz, we work with our engineering group upstairs, and the unit will go upstairs for its final calibration from 65 to 100 gigahertz. So here we have a thermal chamber, and for certain oscilloscopes, we need to do calibrations at different ambient temperatures, starting at 20 degrees C, 25 degrees C, 30 degrees C, 35 degrees C, and 40 degrees C. So what we'll do in this oven, we'll index 5 degrees C, and we'll do some calibration sweeps to see how the product reacts to temperature. We store those as kind of like calibration constants, and as the ambient temperature might move for the end user, the oscilloscope will stay in calibration based off of their ambient conditions, because we built those calibration constants in. So we know the ambient temperature, we know the inside temperature, and we can choose the right calibration curves to compensate for that.
And there you have it, there was the factory tour. I hope you enjoyed it, and this concludes this episode. I hope you enjoyed the whole episode. There was a lot of really interesting material and a lot of interesting discussions that went into it, and a lot of effort on everyone's behalf, and I'd like to thank Teledyne LeCroy for putting this together. This is definitely a very good, very nice gesture on their behalf to show and share the knowledge they have and the experience they have in building world-class instruments. So if you like it, please make sure you leave a comment, give it a thumbs up, and if you happen to buy a $1 million oscilloscope from LeCroy because you saw this video, let them know. I'm sure they'll appreciate it. So until next time.